Okay, welcome to the lab here. We'll get started in just a second. Again, as we mentioned at the end of lecture, what I've decided to do for today is we're going to continue to lecture to kind of put us on pace or a little bit back on track, especially helpful for the experiments coming up and so forth, so that hopefully we get to obviously the material. So again, we're not going to just abandon today's experiment. I'm thinking since Monday's experiment is similar in fashion, it's a buffer experiment as well. Probably on Monday, we'll probably do both experiments or again, parts of both experiments. And that at least will, by Monday, obviously, hopefully after today, we'll get into obviously buffers and stuff like that. So again, just to put us back on track. Again, like I mentioned before, what we're going to talk about for sure at this point on will not be on tomorrow's exam. And I will tell you what will not be on tomorrow's exam from what we talked about earlier as well, once we're all done here. So, in terms of lecturing. So, um, just keep that in mind. What we're talking about now, not going to be on today's exam or tomorrow's exam. Today's exam, that's even better. Let's take an exam right now. But we'll go over for sure at the end exactly what's on the exam and what will not be on this exam, but most likely will be on probably the exam too and stuff like that. Okay, so before we get started here with the last little bit of chapter 14, I think that we should talk about. Was there any questions on hydrolysis, salts, or any of those things? So as I mentioned before, you do need to be able to correctly write those equations. You need to be able to figure out the pH of salts. Um, any questions on any of that stuff? Okay. So we're going to go back to where we skipped, and what we skipped was right here. And we're going to talk about polyprotic acids and sort of how to take care of the sort of calculations that involve polyprotic acids, how they are a little bit different and maybe the same in the sense of some other ones. But let's take a look at some of this polyprotic type acids. So again, here I'm just going to move a few things around. There you go. So polyprotic acids basically means that there are basically more than one H plus that will come off an acid when it dissociates. And there's really monoprotic acids, like we sort of been talking about a lot of them, which is like your HCl. When it breaks apart, you get one H plus and Cl minus. There's diprotic acids, which basically have two H pluses, so H2SO4, for example. Sulfuric acid is an example of that. And as we talked about, I think when we're doing conjugate acid base pairs, these do come off one at a time. So the first thing that would happen is it would lose one H plus and make this. Then the next thing that would happen is that guy there would drop off another H plus and make another guy come off in a stepwise fashion. A triprotic acid is something like phosphoric acid, where obviously it has three H's that can come off. And again, each of them do come off one at a time. And for each of the H's to come off, there is a K value associated with it. So that's what we see here. Ka1 is the first H that comes off. Ka2 would be the second H, and obviously Ka3 would be the third H that would come off. And as we might have mentioned earlier as well, it is much harder to remove the second H than the first one. And then obviously if you get to the third H, it's much harder to remove than the second H. And we see that reflected in our K values. This is for phosphoric acid is 10 to the minus 3 for that first H to come off. Then it's 10 to the minus 8 for the second one to come off. The K value gets much smaller, which means when the second H comes off, it's mainly staying together. Not a lot of it's coming off. And it gets even smaller in terms of the K value as you go to the third one, if you do have a third H to come off. Now, sulfuric acid is a strong acid, and that's why it doesn't really have a K value for the first H that comes off, but the second one that comes off is a weaker acid, and you do have an actual value for it. So this 1.2 times 10 to the minus 2 would be representative of this part of the dissociation process happening right here and stuff. Again, the first part is sort of considered a strong acid. So when we have sort of H pluses coming off in a polyprotic acid, again, it's a stepwise fashion. And what that means is in most cases outside of sulfuric acid, for example, you can have a K value for each of the steps along the way. And like I said, it does typically get harder and harder to remove those H pluses as you continue down that path. Again, because as you continue to remove the H pluses, as you can see here, you start making things with negative charges. And obviously that's going to hold the positively charged H plus a little bit tighter. So that's the typical pattern that we see, that the Ka1 is usually larger than the Ka2. That's larger than the Ka3. So let's take a look at a sort of a problem that involves this and sort of how you go through it. So what we're going to do here is kind of change this problem just a little bit. We want to find the pH. We also want to find for this problem, I'll just list it up here. We want to find the H plus concentration. We want to find the concentration at equilibrium of phosphoric acid. We want to find the concentration at equilibrium of H2PO4 minus, HPO4 2 minus, and PO4 3 minus, or phosphate, and obviously the pH. So we're going to mix it up just a little bit here, and that's just what we're going to look for, is everybody's concentration here. So when we see Ka1, Ka2, Ka3, again, that's the stepwise dissociation that occurs. So again, our H3PO4 is going to break apart first off into H plus and H2PO4 minus. And again, that Ka1 would be associated with that reaction. Again, that H2PO4 minus will then break apart into H plus clean it up a little bit there, give it a try again. We'll break up into H plus and HPO4 2 minus, and that would be the Ka2 that's associated with that reaction. And lastly, what will happen is that HPO4 2 minus will break apart into H plus and our phosphate. And that would be represented by Ka3. So we're going to use each of these stepwise dissociations to help us determine each of the values that we're looking for up here. And what I'm going to do is I'm going to kill my camera so I can actually see a little bit more of my screen without boxes on it. There we go. And let's do that there, I think. All right. And move that out of the way. Now I can maybe see. Perfect. I can see some screen, so that's good. All right, so the first thing we're going to look at is really the first dissociation, which is going to involve this guy here. So the first thing we want to start with, and we kind of want to approach it the same way as a normal sort of Ka type problem, we're going to do an ice table, and we're going to basically try to figure out some concentrations as we get going here. So we'll start with the first one, which is H3PO4, breaking apart into H plus and H2PO4 minus. And again, that's going to be our Ka1 value associated with that, which is 7.5 times 10 to the minus 3. We're going to do an ice table, so the only value we're given is 5. So we're going to do zeros for these guys. We're going to do our minus x, our plus x, and our plus x, which means at equilibrium we have 5 minus x, x, and x. So the ice table here is just like all the other ones that we've done. We're going to go into our Ka1 expression, which is our products over reactants. And we're going to stick our numbers in there. That's going to give us x squared divided by 5 minus x equals 7.5 times 10 to the minus 3. We're going to assume that x is equal to 0. That's going to give us x squared over 5 equals 7.5 times 10 to the minus 3. We're going to multiply the 5 to the other side and take the square root of it. And that's going to give us an x value of 1.94 times 10 to the minus 1. We do want to check it, so we're going to take that number, we're going to divide it by 5, times it by 100, and we get 3.87, which means it's good. Yeah, so the check is good here. So again, you want to make sure that you do check it. So what does that mean? If we go to our ice table, we now have several of these answers we're looking for. We see that x equals the concentration of H2PO4 minus, and that also equals the H plus concentration, and that has a value of 1.94 times 10 to the minus 1 molar. We also can find the value of our phosphoric acid. That is equal to 5 minus x, which would be 1.94 times 10 to the minus 1. And that's going to get us 4.81 molar. So just from the very first dissociation, we have several answers sort of given to us. We have the H plus concentration at equilibrium. We have the phosphoric acid concentration at equilibrium, and we have the H2PO4 minus at equilibrium. Any questions on that so far? All right, so we still need to find a few more answers, so we're going to continue on. And we're going to now look at the second dissociation. So if we look at the second dissociation, that is our H2PO4 minus breaking apart into H plus and wow, I did not like that move again. That was a good HPO4 2 minus. Sorry about the extra line. Just for some reason does not like certain things. So what we have going on is the second ice table. And now you may ask yourself, like, where do I get my initial concentrations from? So where we get our initial concentrations from in our second ice table is from our first ice table. So from our first ice table, we have the equilibrium concentrations of these guys. That means that when we come to our second ice table, we know that we have 1.9, what was that number there? 1.94 times 10 to the minus 1 of that guy. Now, when we get to the H plus, at the end of the first ice table, we also had H plus there, which is here. So we had both of these guys out there, which means when we get to the second dissociation, we also have it, which is also 1.94 times 10 to the minus 1, and this would be 0. So our equilibrium concentrations from the first ice table will now become our initial concentrations in the second ice table. Any questions on that so far? The rest of the ice table here is going to be like normal. We're going to do a minus x plus x, plus x on this side, And that means that when we reach equilibrium, 1.94 times 10 to the minus 1 minus x, this is going to be 1.94 times 10 to the minus 1 plus x, and this is going to be x. This is going to go into our Ka2 expression, and our Ka2 value that we see there is 6.2 to the minus 8. So Ka2, 6.2 times 10 to the minus 8. There's a big minus sign there, right? All right. There we go, and this is 2. So the Ka2 will be our products, which is H plus, HPO4 2 minus, and our H2PO4 minus, again equaling our 6.2 times 10 to the minus 8. We're then going to put our equilibrium guys into our expression. So that's going to give us 1.94 times 10 to the minus 1 plus x times x divided by 1.94 times 10 to the minus 1 minus x, and that's going to equal 6.2 times 10 to the minus 8. Now, at this point, we could assume that x is equal to 0. And that's going to give us 1.94 times 10 to the minus 1 divided by 1.94 times 10 to the minus 1. And we're going to have times x on top equals 6.2 times 10 to the minus 8. I think I could do that math. That's going to cancel. And that's going to give us an x value equal to 6.2 times 10 to the minus 8. It's not like that minus. We do need to check it to make sure it's okay. So we're going to take our 6.2 times 10 to the minus 8. And we're going to divide it by 1.94 to the minus 1. And when you do that, times it by 100, you get something like 0.00003%, which means, again, here, the check is good. So let's talk about what happens in what we just found. We just found this concentration, which is what we were looking for. HPO4 minus 2 minus will equal X, which equals, in this case, 6.2 times 10 to the minus 8 molar. And if we look at our little table, that is going to take care of this guy. So what happens to our H plus concentration and our H2PO4 minus concentration? If we put this X value back into here, the number absolutely does not change. It remains the same. So those concentrations are still going to be, even at this point, 1.94 times 10 to the minus 1. So again, If you put that into your calculator, 1.94 to the minus 1 minus 6.2 to the minus 8, you get 1.94 to the minus 1. Again, it does not change here because it's so small. Any questions on the second sort of step there? Now, we do need to actually go to the third step because we are still looking for the phosphate, and phosphate only happens in that third step. So we will go through the third step now to see what happens for our phosphate. So let's go maybe a fresh page. So at this point, we're looking at this dissociation. So we got this. And again, this is our third dissociation, which is going to be our Ka3 value. And again, our Ka3 value should be 4.8 times 10 to the minus 13. Just like the previous table, where we're going to get our initial concentrations are going to come from our equilibrium concentration. So we could see that our equilibrium concentration of this guy is here. So we're going to put that in as our initial. So getting old, that was 6.2 to the minus 8. We also still have H plus floating around. And as we just talked about, this number here does not change. So it's still 1.94 times 10 to the minus 1. And this would be 0. Now, the rest of the ice table is going to be just like normal. Change is going to be minus x. We'll have our plus x and our plus x. And at equilibrium, we would have 6.2 times 10 to the minus 8 minus x. We will have 1.94 times 10 to the minus 1 plus x. And we will have x that will come down. This is going to go now into our third equilibrium expression for this polyprotic acid. And that's going to be Ka3 equals our products, which is our H plus, times our phosphate, divided by our reactant, and again, that's going to equal our 4.8 times 10 to the minus 13. So just like we did before, we're going to put our equilibrium guys in. And when we do that, we will get 1.94 times 10 to the minus 1 plus x and x. We will then be dividing that by 6.2 times 10 to the minus 8 minus x. And that's going to equal 4.8 times 10 to the minus 13. We might as well continue our assumption here that x is equal to 0. It seems to be okay. So when we do that, that's going to reduce that down to 1.94 times 10 to the minus 1 times x divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. We're going to multiply the 6.2 to the minus 8 to the other side. and then divide by our other number. So we're going to divide by 1.94 to the minus 1. That's going to give us 1.53 to the minus 19 for x. We again want to check it, so you can pick any number you like. We're going to take it and divide by 1.94 to the minus 1, times it by 100, and you're like 7.9 times 10 to the minus 17%. So that is good. Let's check. And again, you can divide it by the 6.2 to the minus 8, or you can divide it by the 1.94 times 10 to the minus 1 to check it. Again, if you do 1, they both should probably be okay. We'll just double check. The other one is all good as well. So what does that mean? That means in this case, the phosphate concentration at equilibrium would be 1.53 times 10 to the minus 19 molar. And when we put that X value back into this table here and here, we also see the same thing. These numbers do not change. So if you take 6.2 times 10 to the minus 8 and you subtract 1.53 to the minus 19 from it, you will still end up at 6.2 times 10 to the minus 8. Same thing with our H plus concentration, 1.94 times 10 to the minus 1 plus the 1.53 to the minus 19 will still give you 1.94 times 10 to the minus 1. So what does this all mean except for 3 screens of calculations? It means a couple of things. What we see in terms of the H plus concentration. Let's just look at that first. When we look at the H plus concentration at equilibrium after the third step, it had a value basically of 1.94 times 10 to the minus 1 molar. If we back up one step and look at the H plus concentration at the equilibrium here, the H plus concentration basically was 1.94 times 10 to the minus 1 molar. And if we look at the H plus concentration after the very first step, it was 1.94 times 10 to the minus 1. What this calculation illustrates with actual numbers is what we were just talking about. It is much easier to take off the first H plus than the second or the third. And more importantly, the majority of all H plus that came off in this example, most of it and almost 100% of it all came off with the first H. And what does that mean if you have a problem that's not exactly like this one, but it's a polyprotic acid and they ask you to calculate the pH of it? What that means is you are almost very safe in most cases to figure out the H plus concentration of the first H plus that comes off, like we did down here. And you could probably calculate the pH directly from that value, and you wouldn't have to deal with the second H or the third H because the majority of all H's that are coming off is that first one. So that means that we can put our H plus into our pH, would be minus the log of 1.94 times 10 to the minus 1, and that would get us we'll go 0.712 on the pH, which I say would be basic. So 0.712 there on our pH. Any questions on any of those parts? So when you're dealing with a polyprotic acid, if you're asked just a basic question of what is the pH, like I said, I probably would just go off of the very first ice table that you do and the H plus that you get, because in a majority of all cases, that's going to be the majority of all the H plus that's going to come off in that acid, that polyprotic acid. So you don't necessarily have to go all the way to the end. We went all the way to the end in this particular problem because of what I asked us to find. I asked us to find the concentration pretty much of everybody, including phosphate, and that's why we had to go to each of the steps to get those concentrations. But if you're just asked a simple, straightforward question, kind of like what the question was asked here, what is the pH of it? You could just go do the first ice table, get the H plus concentration, and you probably will have the right pH at that point. Any questions on how to deal with polyprotic acids? Okay, so that actually is the end of this chapter. I believe that should be everything. I don't think we missed anything. Perfect. Any questions on anything in this chapter here? And again, we're going to continue now lecturing into chapter 15 about, we're going to talk about buffers and stuff like that for a little bit. And then again, we'll talk about what will be on, obviously, the exam from all this stuff. Any questions on any of that before we continue? Again, like I said, the notes are up there on Canvas. If you need them or didn't see them, you should be able to find them there if you want to go grab them real quick while I get this guy set up. No, we don't usually refer to them as sort of that. And I'll answer your question in just a sec. Hang on one sec here. Okay, so hopefully you have these notes and stuff. And again, we're just going to kind of get going on this to put us in a good position for the labs coming up and all that kind of stuff. And again, for sure, 100% for sure, nothing here we're going to talk about will be on the exam. And by the way, the polyprotic acids will not be on the exam either, this coming exam. So again, we'll talk about earlier stuff in just a bit. So chapter 15 is going to deal with buffers and titrations. And it usually is the hardest chapter for most people because conceptually speaking, you do have to sort of understand what is going on in these problems to do the math correctly. There will be a lot of places where you could do, again, all this wonderful math. There's lots of numbers available for you to do math with, but you'll get it completely wrong because that's essentially not what is going on in this particular problem. So let's start talking first off about the idea of what is known as the common ion effect. So the common ion effect is pretty much what the name implies. It implies that we have a solution that within that solution, there is an ion that's in common. So what is it in common with? What we're talking about here is either a weak acid or a weak base that's in solution. And why it's important it's a weak acid or a weak base in solution is it will set up an equilibrium. So for example, if we take acetic acid, which is a weak acid, and everybody's favorite example when we start talking about kind of buffers, right? So if we take acetic acid in solution, if it's in a beaker or wherever you put it, it will basically set up this equilibrium here. Our acetate plus our H plus. Okay. And again, why we're dealing really with weak acids and weak bases is because they will set up this equilibrium. If you threw something like hydrochloric acid in there, there's going to be no equilibrium set up, right? Because it's a strong acid. It's 100% going to break apart into ions. So in a solution or a beaker by itself, that's the equilibrium that's going to get set up. Now, if we have acetic acid in a beaker and we perhaps add some acetate to it, for example, So let's say we put this acetic acid in a beaker with some acetate, like sodium acetate or something like that, right? So we'll do like a sodium acetate. When we put sodium acetate in there with it, like the example on the bottom, that sodium acetate is going to break apart into two ions. One is sodium, and oddly, one is acetate. And sodium acetate, which is a salt, and most salts are pretty much strong electrolytes, which means when they go for a swim, they're going to 100% break apart into ions. So it is not going to set up an equilibrium. So the only thing in that beaker of acetic acid and sodium acetate that's going to technically set up an equilibrium is the acetic acid part. So now you have this acetic acid that set up this equilibrium, and you've also added some sodium acetate to it. And essentially what you are doing is adding more acetate to that equilibrium. And our good friend Le Chatelier's principle should tell us that what's going to happen is if we added more acetate, which is on the right-hand side of the equation, we should expect the equilibrium to shift to the left. And when it shifts to the left, that's going to force more of the acetic acid to actually stay together. And that's what it means when it says it suppresses the ionization of a weak acid or a weak base. A weak base will happen the same way, basically. You'll have a common ion. It will prevent that weak base from breaking apart. Any questions on that? So the presence of this common ion will have the effect of, again, preventing that weak acid from normally breaking apart like it would. So what does that really mean in terms of something like pH, right? So in terms of pH, if we had just our acetic acid by itself, again, it's pretty much free to break apart into our acetate and our H+, which means acetic acid by itself will produce a certain amount of H+. And what will happen, though, if you put that acetic acid in with the acetate, because it's going to cause this equilibrium to shift to the left, that means that in the second solution, the solution with the acetate, we would actually have less H+ being produced or free in the solution. And when the concentration of H+ goes down, in terms of the pH, you should know that the pH goes up. Now, it won't go basic or anything like that, but in comparison to the original pH of just the weak acid by itself to the pH of the weak acid with a common ion, you will see a rise in the pH in that particular case. And the same thing would happen with a weak base. In the presence of a weak base and a common ion, that will cause the concentration of OH- to decrease. And when the OH- concentration decreases, the pH will go down compared. So the same effect will happen with a weak base, except that, again, it will prevent more OH- from being formed and thus have the pH actually go down. Again, most likely will probably not go all the way down acidic-wise, but again, it will go down in comparison to where the pH of the weak base started to the comparison of the weak base with the common ion. Any questions on that? So if we look at an example here of two problems, and we'll go through this together to sort of see it. If we want to calculate the pH of 0.2 molar acetic acid first off, and then second to that, we want to calculate the solution that contains 0.2 molar acetic acid and 0.3 molar sodium acetate, what the pH is. So let us start with the the first one there, which is 0.2 molar acetic acid. So A is acetic acid by itself. Gonna break apart into H plus and does not like that line, I don't think. Acetate. Boy, that's annoying. Do that there. Kind of clean up our little mess here. Yeah. There you go. All right, just fill that back in, give it a try, see if it doesn't mess it up. So like an A-ish there. H plus and a C, H3, C minus, and a Q. Okay. Good thing they invented erasers, I suppose. All right. So initially here again, we're doing 0.2 molar. So initially we have 0.2 molar, 0 and 0. Change is going to be minus X, and plus X. And that means when we do reach equilibrium, we're going to get 0.2 minus X, X, and X. Definitely does not like this slide, does it? Give me 1 second. Let's see if maybe I could do something here. Why don't you continue to work on that problem while I try to fix a couple of things, see if I can get it to work a little better here. Okay, let's see if that's maybe any better. I doubt it, but let's take a look. So again, this can go into our K expression, which is our Ka. That's going to be our products. Divided by our reactants. Again, I apologize by the extra lines here. And that's going to equal our Ka value, which was 1.8 to the minus 5. Ignore the really big lines. They're not meaning anything. So putting it in, we will get x squared divided by 0.2 minus x equals 1.8 times 10 to the minus 5. And we're going to make an assumption that x is equal to 0 and hope for the best here. Let's see here. We're good. So we're going to assume x is equal to 0. So it will give us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. Multiplying the 0.2 to the other side times 1.8 to the minus 5, taking the square root of it, gets us 1.9 to the minus 3 for x. And we do want to check it, so we're going to divide it by 0.2, times it by 100, and that's going to equal 0.9%, which means we should be good in terms of that. That means that the check is good. And importantly, when we go to our table, we see that the H plus does equal X, which means that the pH in this case minus the log of 1.9 times 10 to the minus 3, that is going to give us an opening pH of 2.72. So the acetic acid by itself will have a pH of 2.72. Any questions on this one? This is just like a regular Ka problem we did in the previous chapter. So that should be pretty good and not too bad for you. Now we're going to look at part 2 there and see what's going on. And just kind of fix that maybe. So in part 2 or part B, we're looking for what happens when we take the same acetic acid, that's 0.2 molar, and we put in there 0.3 molar sodium acetate. So in this particular one, we're going to have 0.2 molar acetic acid, and we're going to put it in with our 0.3 molar sodium acetate. So this can be a little bit different. So when we look at this, we can see it through all the dots there. When we look at the sodium acetate part, it is going to break apart into sodium ions and acetate. And the only thing in this mixture that when you put these together that's going to actually set up an equilibrium, the only thing that's going to do that is the acetic acid. So in terms of sort of the ice table, which is what we need to do, the ice table would be set up based on the acetic acid because that's the only thing that's going to basically set up the equilibrium. So if we take our acetic acid, just like we did on our previous problem, we're going to set up our ice table, and initially we do have 0.2 of that guy. Now, H plus, we have 0. Now, what about the acetate? In case of the acetate, we actually do have an initial concentration of the acetate, and that's going to be supplied by the sodium acetate here. And it's the sodium acetate that's going to supply our initial source of acetate. So since this whole thing was 0.3 molar, our acetate, because it's a 1-to-1 relationship, will also be 0.3 molar. So we will have an initial concentration of this guy. And that's where a lot of people will mess up, is they will put 0 for that guy. And in this case, because it's a common ion, there is the acetate being present from the sodium acetate that was put in there. And we do need to make sure we include it on the initial line. Otherwise, again, you will get the wrong answer. If you leave it as 0, you're essentially redoing this problem here that we did in part A. So you got to make sure that you do have that common ion present in the initial line. Rest of the table will be very similar. We're going to do minus x. We're going to do plus x. We're going to do plus x. We're going to get to the equilibrium, which is going to be 0.2 minus x. This is going to be x. This is going to be 0.3. The key here as well is it's plus x, which sometimes people will mess up on as well. Any questions on this ice table? So really the main difference in the place where most people, for a lack of a better word, will screw this up. Yes, it will be right there. They will put that as 0. And again, if you put that as 0, you're not doing a common ion problem. You're essentially doing just a weak acid problem. So just like normal, we're going to go into our equilibrium expression here. And again, this is going to be Ka. And it's going to be our products, which in this case will be x times 0.3 plus x divided by 0.2 minus x. And that's going to equal our Ka value. And the other thing that people sometimes get confused on is it is still the same Ka value as we used in part A. And that's because it is still acetic acid here. And they would still use the acetic acid Ka value, which is at 1.8 times 10 to the minus 5. We're going to assume that x is equal to 0 like we did on the previous one, since it seemed to work. And that's going to get us x times 0.3 divided by 0.2. And that's going to equal 1.8 times 10 to the minus 5. We're then going to multiply the 0.2 to the other side. We're also going to divide by the 0.3. As soon as I get rid of some of these extra lines. So this was a 5. And if we do that, we will get 0.2 times 1.8 to the minus 5 divided by 0.3 gives us 1.2 to the minus 5. So 1.2 to the minus 5 for our x. And again, if we check it, we're going to take that and divide it by 0.2, times it by 100, for example. And you get something like 0.006, which means it is good. The check. That also means if we go to our table, we see that H plus equals X. That means that the H plus concentration equals 1.2 times 10 to the minus 5. And that means that the pH, we could put that directly in, will equal 1.2 times 10 to the minus 5, or minus the log of that would be good. So minus the log of 1.2 times 10 to the minus 5. That gives us 4.92 as our pH for this solution. Any questions on that calculation? Okay, so let's take a look at sort of the comparison of the two. The pH, when we had acetic acid by itself, nothing in it, just the regular weak acid, able to set up its equilibrium, had a pH of 2.72. When we took the exact same weak acid, same concentration as the previous one, and we added to it some sodium acetate that had a common ion present, we see that the pH goes up to 4.92, higher pH. And that is because if you compare the H plus concentrations in both of them, the H plus concentration in the first one was 1.9 times 10 to the minus 3. In the second one, it was 1.2 times 10 to the minus 5. So what we saw here in this example is because of the common ion, it causes equilibrium to go to the left. And when it went to the left, it kept this weak acid together. And it basically kept it together more than it did before. And because it kept together more, we had less free H plus in the solution. And that resulted in the pH becoming higher, which is usually always the case when you're dealing with a common ion. Any questions on any of that there? Okay. So these type of problems that involve common ions are essentially buffers that we're going to talk about here in a little bit more detail in just a second. But when we have these sort of common ion problems, if you look at the initial concentration and you look at the equilibrium concentration, so essentially if you take the X value that we just got in the previous problem and put it back in to the equilibrium line, what you would see is that the initial concentration of the weak acid and its conjugate base basically will pretty much be the same at the beginning in the initial entry and the equilibrium entry. So it does not change very, very much from beginning to end. And that's important because what that will allow you to do is you can actually use an equation instead of an ice table to figure out the pH. And that equation is what is known as the Henderson-Hasselbalch Equation, which is derived, as we see here. You don't have to worry about deriving it. But the Henderson-Hasselbalch equation is the equation that is in that box on the right. And it says that the pH of a solution is equal to the pKa value. So to solve for the pKa value, you take the pKa is equal to minus the log of the Ka value, plus the log of the conjugate base over the acid. So we actually can use this formula, the Henderson-Hasselbalch formula, to calculate the pH of our previous problem. So for example, our previous problem, we had our acetic acid, which was 0.2 molar. And we had our sodium acetate, very bad today, huh? Which was 0.3 molar. And we can use that pH is equal to our pKa plus the log of the base divided by the acid. Now, when we're comparing these two, the acetic acid to the sodium acetate, obviously the name of this guy is acetic acid, which would tell you it is the acid part. So we can go right into our pH equation. We do need to figure out the pKa value first. So again, the pKa value is minus the log of the Ka value. So pKa is minus the log of the Ka value, minus the log of the Ka value. So minus log of our 1.8 times 10 to the minus 5. And that gives us a pKa value of 4.74. I'm going to go back to the other page here and write it here. So pKa equals minus the log of 1.8 times 10 to the minus 4. That's going to give us a pKa value of 4.74. And now we could actually put it into this equation. So the pH would equal 4.74 plus the log. Again, our acid is the acetic acid, which was 0.2 in that previous problem. And our base was the sodium acetate, which was 0.3. So we would want 0.3 divided by 0.2. So if we do that, we get 0.3 divided by 0.2, take the log of it, plus 4.74 gives us a pH of 4.92. So you can see here we did get the exact same pH as we got in this problem, 4.92. We didn't have to do an ice table. We could go right into the Henderson-Hasselbalch equation, and you could actually get it. A couple of things that you should be aware of. The Henderson-Hasselbalch equation is only used for common ion situations, and really those are for us buffer situations. So you should only use the Henderson-Hasselbalch equation in a buffer situation. So you don't want to use it in any other situation. So there is another version of the Henderson-Hasselbalch equation that is sometimes used and you sometimes will see, and that version is that the pOH is equal to the pKb plus the log of the acid divided by the base, where the pKb would equal minus the log of the Kb value. So sometimes people will use this formula when you're dealing with kind of like a basic buffer. I personally don't see the purpose of it because in most cases, you're asked to calculate the pH, which means if you use this equation, this is the pOH, which means you eventually got to subtract 14 from it anyway. So you can use the Henderson-Hasselbalch equation for acidic solutions, basic solutions, doesn't really matter. I personally would stick with the Henderson-Hasselbalch equation. Again, though, sometimes you will see this equation, but remember, it is the pOH, which means you need a pKb, and the acid over base. So it's the opposite than base over acid. So you'll sometimes see that. But sometimes a good relationship to remember is if you take the pKa value plus the pKb value, it will actually equal 14. So sometimes you may need a Ka or a Kb. And if you know the pKa or pKb value, again, you can find the other one because pKa plus the pKb will equal 14. So that's a nice relationship that is sometimes used as well. Is your question, why is it, are you asking why the pKa value is not 1.8 times 10 to the minus 5? So if that is what you're asking, why the pKa value is not 1.8 times 10 to the minus 5, when we use this formula, the pKa is different than the Ka value. So the Ka value is 1.8 times 10 to the minus 5. But when you convert it into the pKa value, you're basically, it's almost like pH. You're taking minus the log of it, and you're turning it into 4.74, if that was your question. It was, yes. I'm sorry. The one I wrote it wrong. Thank you. My bad. There you go. Thank you. I had the right value there, but I wrote the wrong thing. Thank you. You're correct. It is 10 to the minus 5. It should still be 4.74. That I didn't screw up on, I hope. Yeah. Thank you. So yeah, we are obviously using the same Ka value from the previous one, which is to the minus 5. Other questions on that? Okay. So this does allow you in these type of problems to really work the problem out two ways. If you're a fan of ice tables, you could continue to use ice tables, but you can probably calculate a little bit quicker using the Henderson-Hasselbalch equation. And again, you could do it either way. They both will give you the same answer. As you can see in this example, you'll end up with the exact same answer regardless of which one that you choose. There are people that just like to do the ice table, so you can, but there are people that like to use Henderson-Hasselbalch. Again, a key thing to remember is you should only use this equation in a very specific time period, and that very specific time period is really a buffer situation. If it's not a buffer situation, which is a common ion situation, you should not use the Henderson-Hasselbalch equation. And that is also where people go terribly wrong in this chapter, is they go, oh, cool, I got two numbers. I'm just going to throw it into the Henderson-Hasselbalch equation in every calculation I do. And you will get a lot of things wrong if you do that. So again, it can save you some time, but it can save you time only if you're doing this specific type of calculation, which is really a common ion problem, but it's most often known as a buffer problem. Okay. Any questions on that? All right. So why don't you take a second here and calculate what is the pH of this solution that contains 0.3 molar HCOOH and 0.52 molar HCOOK. Ka value for the formic acid is 1.7 times 10 to the minus 4. So take a couple minutes and then we'll talk about it. Okay, so let's take a look. So basically we got two things here, and this is the Ka value from the acid, which is over here. And we do know that that's the acid. A couple of ways you could determine it. That sometimes also gives people a little difficulty, you know, which one's the acid, which one's not the acid. So typically the acid, right, is something that can donate an H+, which means when you're comparing the two, it's probably the one that has more H pluses. So if you look at HCOOK versus HCOOH, the second guy there that I said has the extra H, which means it's an acid. Also, typically acids won't have these sort of spectator ions in it, like sodiums, potassium, lithiums and stuff like that. So usually those guys are your kind of conjugate bases and stuff like that. So again, that's a way you could quickly sort of determine. In this particular problem, didn't really tell you which one was the Ka. They just assume that you looking at it will be able to figure that out. So again, the HCOOH, which is formic acid, actually has the extra H in there, and that would definitely make it the acid in this case. That also means that that Ka value goes for that guy. And in terms of both of those things here, that would technically be the only thing that would set up an equilibrium, and it would be the and it'll break apart into H plus and our HCOO minus would be what would be set up the equilibrium. This is what the Ka value would be for. And if you chose to do an ice table, the ice table would be based off of this guy here. We have obviously our initial concentration of it, which is 0.3. We would have 0 of the H plus to begin with. But now this is a common ion because we do have this guy here. So that guy is going to break apart. And when he breaks apart, he's going to break apart into HCOO minus and K plus. It is this ion here that is the common ion that we see over here. So we do need to get the concentration of it, and it is going to be 0.52 because it's a one-to-one relationship, and that means we should have an initial concentration of 0.52. This would be minus X plus X, use the scribble, and plus X. That would give us 0.3 minus X, X, and 0.52 plus X. So if you chose to do the ice table, this would be sort of what it would look like, hopefully with a lot less of those big lines coming through it, but it would sort of look like this. You then would go into the Ka expression like we've done before. You would solve for X. X would equal your H plus concentration, and that would get you to your pH. Now, if you recognize that this is a common ion problem, you could avoid the table altogether, and you don't have to actually do the table. You could use the Henderson-Hasselbalch equation. And again here, the Henderson-Hasselbalch equation would be the one that we saw on the previous page. So it'll be pKa plus the log of the base over the acid. We do need to calculate the pKa value. So the pKa value would be minus the log of 1.7 to the minus 4 on this one. And if we do that, it looks like we get 3.77 as our pKa. That means that the pH, fancy pH, 3.77 plus the log. Our base, again, is going to be the potassium formate, which is this guy here, 0.52 on top, divided by our acid, which is 0.3. And if we do that, 0.52 divided by 0.3, take the log of it, and add 3.77, we get something like 4.01 as our pH in this case. And again, if you went through the ice table, perfectly fine to do. You should end up with pretty much the same answer. So again, you do have two ways to do it. In this particular case, if you could recognize that it is a common ion. And again, I don't know, the Henderson-Hasselbalch would probably be a little bit quicker But again, if you can't remember, if you're not sure you should use it, you can always default back to your ice table. And again, though, the important part of it, again, is right here. You need to make sure that you do have an initial concentration for that guy on that side. Otherwise, again, you'll just be doing the weak acid. Any questions on the Henderson-Hasselbalch here in a common ion, which again is essentially a buffer problem? Okay. Then let's actually talk about buffers and really what a buffer is and sort of how a buffer works, if you will. So a buffer is a solution that basically, first off, is made up of a combination of really two things. It's made up of a combination of either a weak acid and its conjugate base. So a buffer is either a weak acid and its conjugate base are the salt of its conjugate base. Or you could have a buffer made up of a weak base and the conjugate acid, or sometimes referred to as the salt of the conjugate acid. It's referred to as the salt of the conjugate acid or the salt of the conjugate base, because if you look at the last example we did, there was like a potassium there, right? And that potassium is basically what balances out the charge and makes it a salt. Now, both of those things need to be in the solution to begin with in order for you to have a buffer. And you cannot have a buffer that is made up of a strong acid or a strong base. And we're going to talk about why that is in just a second, but it does need to be consisting of either a weak acid and its conjugate base or a weak base and its conjugate acid. But you cannot have a buffer that is truly made up of a strong acid or strong base. You can, though, make a buffer from a strong acid or base, but that strong acid and base will be gone by the time the buffer is made. So you cannot have a strong acid or base as part of a buffer. A buffer will essentially resist changes in pH when you add acid or base to it. And when we talk changes in pH, we're talking about pretty big changes in pH. So if you have a buffer, first off, though, a buffer is not a neutral solution. So sometimes people like to think a buffer is a neutral solution. A buffer is not a neutral solution. A buffer could be a neutral solution just as much as a buffer could be an acidic solution and a buffer could be a basic solution. You can make a buffer at any pH you choose, anywhere from 0 to 14. You could lay yourself up a buffer solution. So sometimes people get in their head that they think a buffer always has to be like neutral, pH is 7, and that is absolutely not the case. A buffer just essentially means whatever pH it starts at. So let's just say you had a buffer that started at a pH of 5. If you took that buffer that started at a pH of 5 and you added some acid to it, as long as everything's okay in terms of concentrations and everything, the pH of that buffer will remain pretty much at 5. Will it go down? The answer is yes, it will go down a little bit. Maybe it goes from 5 to like 4.9 or something like that. So it will go down a little bit if you add acid to it. But what you will not see is you will not see a tremendous jump in the acid concentration in the pH when you add the acid. So for example, if you add acid to the buffer, you won't see the pH go from 5 to like 1. So you won't get that really big jump in pH. But it will go down a little bit. So if you put a pH meter in it and you're monitoring the pH and you add some acid to it, you will start to see the pH go down. But you won't see these big jumps in pH. Now, same thing if you took that buffer that was at a pH of 5 and you added some base to it. The pH will maintain around 5. It may go up a little bit. Maybe it goes to like 5.2, 5.1, somewhere in there. But you won't see the buffer jump from like a pH of 5 to a pH of 13 if you add base to it. Now, if you add base or acid to a non-buffer situation, you will expect to see a big jump in pH when you do that. So let's really talk about, why that happens. Why do we see jumps in pH? Why in certain cases we don't see jumps in pH when we use buffers versus non-buffers. So let us take a look here. So when we look at sort of a buffer, and let's take a look at what happens when, for example, we don't actually have a buffer. So let's look at a non-buffer situation. Give me one sec here. Now, if we take water, which is not a buffer, so if we take some water here, not a buffer, and we add some hydrochloric acid to it. When we add hydrochloric acid to just water, what's going to happen is the HCl, right, will 100% break apart into H plus and Cl minus. And what we would expect to happen in this case is we have just generated a lot of free H plus. And remember that the pH of a solution is minus the log of the H plus, which means what we just did is we increased the H plus concentration a lot very quickly. And that means we should see the pH really start to drop very quickly as well. So, for example, if we started with a pH of water, we'll just say it was 7, and we add some hydrochloric acid to it, we may see the pH go from 7 down to maybe a pH of 2, maybe a pH of 1, depending on how much we add. And we see that big jump because we've just generated a lot of free H plus very quickly in that case. Now, what happens if we take water and we add some sodium hydroxide to it? Sodium hydroxide, which is a strong base, will break apart into Na plus and OH minus in water. And what we just did here is we just produced a lot of free H plus. And that's important because if you remember, the concentration of H plus and the concentration of OH minus, they are related to each other. So as the concentration of H plus increases, the concentration of OH minus decreases, and vice versa. As the H plus concentration decreases, the OH minus concentration increases. So in this situation, we created a lot of free OH minus very quickly, which means the OH minus concentration goes up, the H plus concentration goes down, and the result of that is the pH will go up. And in this case, same example, if we started, say, with water at a pH of 7, we add some sodium hydroxide to it, we would expect to see a big jump in pH headwards upwards because we're adding base, and maybe it goes from 7 to like 13 or something like that, and we see a very, very big jump. So water, which is not a buffer, basically will allow the production of free H plus, which will have a very big effect on the pH of a solution, while when we add sodium hydroxide or something such as that to it, we'll produce a lot of hydroxide, which also will have a pretty big effect on the pH. So why does that not happen with a buffer? Let's find a place where I could write. Maybe I'll write here. We'll see. I'll write here on this page here. Maybe I'll find a good spot to write. Actually, I'll write on this page because I think it might help with the weird lines that we keep getting. Let me try this page here. All right, so let's give this a go here. So now let's say we took an actual buffer, so something like acetic acid and sodium acetate. So we'll take this combination, which is everybody's favorite example for a buffer. Acetic acid is a weak acid. Sodium acetate is his conjugate base, or the salt of his conjugate base. What makes it the salt is the sodium part. The conjugate base is the acetate, but the sodium there is to balance out the charge. And again, that makes it an ionic compound and makes it basically the salt of it. And when we look at this buffer, there really is two parts. There is the acetic acid part, which is the acid part of the buffer. And there's this sodium acetate in this particular example, which is the base part of the buffer. And just so we're clear, when you toss it in and when we're starting, you have both of those things floating around in the solution to begin with. Oops. So you have both of those guys in the solution to begin with, which is what makes a buffer. So let's do the exact same thing as what we did previously. Let's take our HCl and add it to our buffer. When I take HCl and add it to the buffer, it's going to react with the base part of the buffer, right? Because that's why they're called acid-base reactions. So the HCl, when I dump it into this buffer, is going to find the sodium acetate and react with it. And when it reacts with this sodium acetate, we will get our acetic acid and some sodium chloride. So when we add our acid to our buffer, this is the reaction that we're getting. Now, a couple of important things that we see on the product side here. We see that we actually made some acetic acid, and acetic acid is part of the buffer to begin with. So we actually made part of the buffer, right? Which means that's obviously not going to mess up the pH because it was there to begin with. The other thing that we made here is a salt. And from our conversation about salts earlier today, you should recognize that salt as being a neutral salt, right? Sodium chloride is neutral, which means it will not have an effect on the pH. The main thing that's really going to allow our pH not to change all that much is actually what we do not see here. And what we do not see here is, if we go back and look at our reaction of our acid in water, we see that when we react the acid in water, we produce a ton of free H plus in water, for example. In our buffer, we don't produce any free H plus. So we basically did not produce any free H plus. So why is that important? That is important because if we didn't produce any free H plus, that means that the concentration of H plus will remain relatively constant. And that is important because if we keep the H plus concentration relatively constant, that in turn should keep our pH relatively constant. And I say relatively constant because in reality, like I mentioned, if you were following the pH, you would see the pH start to move. But it will not be a tremendous jump in pH. So one way a buffer is able to maintain the pH when you add an acid to it is the base part of the buffer will react with the acid you're adding, And essentially what it will do is prevent the formation of free H plus in that solution. And because it does that, it allows the H plus concentration to remain relatively constant. And in turn, that allows the pH to remain relatively constant. Question on adding an acid to a buffer. We then will talk about what happens if we add a base to a buffer. So let's talk a little bit about that here. Let's get maybe a different color. Now, if we add a base, come here, to a buffer, we will use the exact same buffer. And in this case, we're going to add sodium hydroxide, which is our strong base, to this buffer. When we add sodium hydroxide to our buffer, because sodium hydroxide is a base, it will react with the acid part. So when the sodium hydroxide comes in, it's going to find the acid part of the buffer and react with it. And when it does, we will get acetic acid. And we're basically going to get a acid-base reaction that's going to occur. So the formation of water is going to happen. And we will get some sodium acetate. Now, same thing happens here. We actually just produced more of sodium acetate, which was part of the buffer to begin with. So obviously that's not going to mess up the pH. We also produce water in that reaction, which will not mess up the pH either. But the same thing as we saw above is actually something that we don't see here, that we did see over here. When we reacted the sodium hydroxide in water, we produced a lot of free OH minus. And because we produced a lot of free OH minus, we did not see that here. So we did not produce a lot of free OH minus. And why that's important is OH minus and H plus are related to each other, like we were talking about earlier. So if our OH minus remains relatively constant, that also means that the concentration of H plus will remain relatively constant. And by default, that will also mean that the pH will remain relatively constant. So in reality, the way a buffer works and how a buffer works is because it does contain an acid part and a base part that's in the buffer to begin with. That allows it, when you add either an acid or a base to the buffer, to basically prevent the formation of free H plus, which would happen if you add an acid, or free OH minus, which would happen if you add a base. And what it essentially allows that solution to do is maintain the concentration of H plus there was in the solution originally. And because the concentration of H plus is relatively constant, you will have a relatively constant pH and you will not see a tremendous jump in the pH of that solution. Question on how a buffer kind of works there. And let's see here. So just to visually kind of show you this, and I'm just looking for a place where I can visually put this. And let's try it here. So if we have a buffer, let's go this way. So if this was our buffer, and again, acid part Just go AP for acid part and BP for base part. So in a buffer, we have, again, this acid part, and we have this base part that is in the buffer to begin with. And a lot of times when you make a buffer, you sometimes want those guys to be sort of equal in concentration, which is sort of why they're drawn equally. Now, if we take to this buffer and we add some acid to this buffer, what we saw is we're going to have to use up some of the base part of the buffer to react with the acid we're adding. And what we also saw was when we add the acid, we're actually going to make the acid part of the buffer. So what's going to happen is, exaggerated drawing, the acid part of the buffer will get bigger and wider apparently. And the base part of the buffer will start to come down a little bit. Now, a similar thing will happen if we add to the buffer a base. So if we add a base, and if we add a base to the buffer like we saw in those reactions that we were looking at, we would expect the base to react with the acid part of the buffer. And when it does so, what's going to happen is the acid part is going to get smaller and the base part is going to get larger. So we'll do this for the base part, and we'll borrow that extra line there for the acid part. So the acid part of the buffer will get smaller and the base part will get larger. So buffers can work really well for sort of a long period of time in a lot of cases because they're almost sort of self-generating. So as you add acid or as you add base, you're basically regenerating part of the buffer as a result of that. But there's also what is known as buffer capacity. So for example, what would happen if I decided, hey, I like adding acid so much, I'm just going to keep adding acid, until the bottle's empty. Why not? So I'm just going to keep adding the acid in there. As you continue to add the acid, what you would see, obviously, is you're going to continue to use up the base part of the buffer. And you're going to continue to use up the base part of the buffer until at some point, you're not going to have really much base part left of the buffer. And it's at that point where if you continue to add the acid, it doesn't stop you. It doesn't deter you. You just keep going. You're going to basically blow right through the buffer part, or I'm sorry, the base part of the buffer. And at that point, it will no longer be able to maintain the pH because at some point, once you get rid of the base part of the buffer, you're now just dumping in a whole bunch of acid that won't react with anything. And you're going to generate a lot of free H+. And it's at that point you will see the pH start to jump and go down tremendously in that case. Same thing would happen if you just continuously added base to a buffer. It would eventually use up the acid part of the buffer, and at some point it would no longer have the capacity to maintain the pH and act as a buffer, and you would start to see a big jump in pH at that point. Other things that are important, as we'll talk about in this chapter, is the molarity of your buffer and also the molarity of your acid and base you're adding. Perhaps if you went to the shelf and you grabbed, say, the 18 molar bottle of hydrochloric acid versus the 0.1 molar bottle of hydrochloric acid, and you decided to add to your buffer, you may just blow right through your buffer because it cannot handle that molarity. So we'll talk a little bit about it, and we'll see it when we start doing some of the calculations that, you can sort of blow through a buffer if it's not made properly. So when we want to make a buffer, we always want to make it sort of properly based on sort of the application And that has a lot to do with the molarity that you want to make of your buffer, and also, again, the molarities of the reagents that you may be adding to your buffer. And when we look at the Henderson-Hasselbalch equation, a lot of times we will try to make a buffer, like I said, with an equal proportion of the acid part and the base part. And if I have an equal proportion of the acid part and the base part, when I look at the Henderson-Hasselbalch equation, that means that this guy would be 1. And if you take the log of 1, that equals 0. And that means if you start out with sort of a equal amount of the acid part of a buffer and the base part of a buffer, the selection of what would make a good buffer for you usually revolves around a pKa value that's equal to plus or minus 1 of your desired pH. So what does that mean? It means if you wanted to make, for example, a buffer at a pH of 4, you would probably want to choose something like acetic acid to make that buffer out of, because acetic acid has a pKa value of 4.74. It's in the ballpark. If you wanted to make that buffer at a pH of 4, you would not want to choose something like ammonium, which has a pKa value of like 9.25. That is very far away. You maybe in theory could do it, but it's probably not going to work very well as a buffer. So sometimes you want to figure out, you know, what do I want to make this buffer out of? What weak acid or weak base would be a really good choice? So usually what you're looking for, again, is a pKa value that's usually plus or minus 1 of your desired pH for your buffer. And that's sort of how you could kind of choose it. Any questions on that there? Okay. I think that's a tremendous amount of torture here for one day, having to listen to 2 lectures in a row, I suppose. All right, so what we're going to do is we're going to wrap it for today, I think. But let's talk about tomorrow, the exam, and all that before we do. Obviously, anything we talked about here in lab will not be on the exam. So definitely nothing from chapter 15. That's going to be the next exam. Polyprotic acids, which is from chapter 14, will not be on the exam either. And what I'm going to do, I think, is, just so we're clear, let me just find a spot here. Let's go back to where we were. No, that is, there we go. So from what we talked about today, we will move salts and polyprotic acids, as it is kind of crossed out, will not be on the exam tomorrow. So from today, you don't have to worry about salts or polyprotic acids. You do need to worry about them, though, obviously. So we will move those 2 topics to exam number 2. So exam number 2 will cover hydrolysis and salts, like we talked about today. It will also cover polyprotic acids, in addition to, obviously, whatever else is going to be on exam 2, which is chapter 15, I think, and maybe 16 as well. So any questions on that? So what you do need to know from today is, so we're clear, you do need to know acid strength that we talked about. So you need to know about acid strength, and you do need to know about Lewis acids and bases and oxides. So that's not too much, I don't think. So that's pretty easy from today, I think. So that's not too bad. So everything is fair game up through yesterday. And from today, that would be, again, you need to know the strengths of acids. You need to know what Lewis acid and base is. And you need to know about just briefly about what we talked about in terms of those oxides. We will move the 2 bigger topics to the next exam, which again will be salts and polyprotic acids. Any questions on any of that? So again, the exam will cover all of equilibrium chapter, the acid and base chapter, again, all the way through everything we did yesterday, which goes through weak acids and weak bases, and then those 2 things from today, or 3 things from today. A reminder that the exam, yeah, and we're going to get to write that. So it's a good question. So reminder that the exam is tomorrow, and I think it's going to be a written exam. So what's going to happen is I will post the exam up on Canvas. You'll be able to download it and print it and work it out, obviously. So if you do have a printer or access, hopefully, to a printer, that would be good. So you could do that. If you don't, then obviously you can do it on a piece of paper, but hopefully you can have a way to print it, I hope. It does need to be handwritten, no typing of anything, obviously, or anything like that. You do have to log into Zoom, and we will have a Zoom meeting, obviously, for the exam, which will be during our lab time. And you do need to have your camera on the entire time. It does need to be focused on your paper and your hands where you're writing, and kind of like your work area, okay? So I can see what's going on in that work area and make sure that there's nothing in that work area or anywhere near it that you should not have. So obviously this is a closed notes exam, closed book exam, and all that kind of stuff. So you do need to have your camera on the entire exam period. It does need to be focused in on you and your area where you're working, so I can see clearly what's going on with your papers and all that kind of stuff. Truthfully, I'm still writing the exam, so right now it has 0 questions. So hopefully by tomorrow, I'll at least have 1 or 2, I hope. But hopefully by then it will have that. Honestly, usually somewhere between maybe, I don't know, 9 to 11 questions. Mostly problem-based type questions is probably what you'll have. But it's not completed yet, so I don't know yet. So what you are allowed to have with you during the exam is what you would be allowed to have in a normal situation if you were in person, which means a writing utensil and a calculator, a non-graphing programmable calculator, a regular old run-of-the-mill calculator, and that's pretty much it. You should not have anything else. Your cell phone should not be out. None of those other type of devices should be out. No notes should be out. No books should be out. None of those things should be out. If I see any of those things out or reached for or anything like that, that will be a 0 on the exam. You will be provided a periodic table and any type of constant values that you need, like K values and things of that nature. So that stuff will be provided for you. You're required to be in front of the camera for the entire exam that you are taking it, which means you should not get up away from the camera view for any reason, for any moment in time or anything like that. So that also means you get a 0 if you move away from the camera and that type of stuff. So make sure that you're in front of it. Make sure that you have to use the restroom. You use it before you take the exam. No restroom breaks or anything like that. We really can't leave the camera view because, I don't know what you're doing if you leave the camera view. So you do have to be there during your whole period. When you're done with the exam, you'll need to upload it like our normal assignments. When you upload it, make sure it's, I won't say visible, maybe it's the wrong word, readable, I suppose is the right way to do that. Make sure it's not too dark or anything like that. If you take a picture, make sure you know it's pretty clear when you upload the PDF of it. So no leaving the area. If you leave the area, I should expect your submission to happen pretty soon after that, right? So if you leave the area, I'm just going to assume that you're submitting something and you're done with the exam. And again, if I don't see the submission, you're going to get a 0. So make sure that you don't do anything dumb like that. Yes. Just in general, make sure you don't do anything dumb like that. If you do have a question, the only thing you really should be reaching for the computer for, I suppose, is to chat with me privately through Zoom if you do have a question. Yeah, so you're going to do kind of the same thing. So you're going to you're going to take a picture, make it a PDF, and upload it. Yeah, so if you are completely done with the exam, again, if I see you reach for your phone to take a picture and scan it in, then I should expect, like I said, your submission to occur pretty quickly. If you don't want to worry about that or worry about that, at that point, if you're done with the exam, you could send me a private chat that says, I'm done with the exam. I'm just snapping the pictures to upload, and then I obviously will understand what I'm seeing. So you're, again, if you leave the camera area to go scan it in at the end, I should expect your scan very, very quickly. Yes. So it shouldn't come in like 30, 40 minutes later or anything weird like that. So, the idea is obviously if you're leaving the camera view to upload it, and I understand that you may need a scanner somewhere or you may need to grab your phone at the end, that is perfectly fine. But I should expect to see your submission very soon after you sort of leave to do that. Not like I'm going to leave the camera view, go look up some stuff and finish my exam and then upload it a long period of time later. In my experience, most people only need a very, very short window of time to upload their work after they complete it. So it really shouldn't be a tremendous amount of time. So if I see it comes in a tremendously amount of time, I'm probably not gonna be happy with that. And if it's a big amount of time, that's going to be a 0 probably. But if it's a little bit later or something like that, and it's a reasonable amount of time for you to go and kind of upload it, you'll be okay. Okay. So, again, we just want to prevent anybody obviously from doing anything dumb or wrong, like, going and finishing the exam outside the picture and go, oh yeah, I just needed the hour to upload it and stuff like that, so it's not my first day, and I have a pretty good understanding of how long it should really take most people to upload these things. And even 20 minutes is sometimes, I think, way too long. So, most people could get it in within minutes of finishing their exam. And that's really what you should try to shoot for, okay? Anything above minutes after submitting the exam, I'm going to be a little not so happy, I suppose, in that sense. All right. By no means should you run around with your head cut off like doing this stuff, but, a prompt uploading of your work is really what should happen. And again, I have a pretty good feeling, because I've done this for a little while here, in terms of uploading and submitting exams and how long, the work comes in, as to what a reasonable amount of time is. Okay. Yeah. So again, there's a little flexibility. Obviously, the exam will be released at a certain period of time to everybody, obviously. If you need to print it, again, it shouldn't take you all day to print the exam or anything like that as well. So again, and what a reasonable amount of time to sort of get your exam printed and get going. Again, if I release the exam, at 1, which is not going to be when it happens, but just for example, I release it at 1 and you don't show up in front of the camera until like 1:45, clearly, that's a little long to print it out, so obviously, you should be there pretty close. So any questions on that? So just so clear, the main points is, do the right thing, essentially, right? So make sure you're in front of the camera all the way through taking it. I could clearly see your work area and sort of your hands and what you're working on. And, don't have anything out. Obviously, you shouldn't have. Just like if you were sitting in the classroom with me, you wouldn't have out all these extra stuff or your phone or anything like that. Once you complete the exam, again, like I said, if you feel more comfortable, you could just shoot me a private chat there that, hey, I'm going now to upload my exam, and then I should have an idea when I should expect your exam to be uploaded. And you should be able to go to Canvas and print it out and, like I said, work in front of the camera. Any other questions on that? And again, the other major thing is during the actual exam taking, no leaving the area in terms of the camera. Again, if you have to use the restroom, make sure you take care of all that before you start. Or otherwise, if you get up to go do that, you better submit your exam at that point. Any questions on any of that? Let me just get a couple of these questions. So, yeah, so a couple of things on that. If for some reason you can't print it, don't have it, you could take a regular piece of paper and work out the problems and stuff like that. You could do that if you don't have access to print it or anything like that, okay? Yeah, so we're gonna try this and see how it works, at least here for the first exam. We're gonna go kind of this way in terms of the proctoring. You know, if there's a lot of issues or anything like that, you know, we may go to the proctorial, but as of now, seems to be the consensus of other instructors as well that we're going to go with this route for this class at this moment. So for the first exam, you obviously don't need to download proctorial or anything like that. I'm going to be your human proctor and watch you as you are taking your exam, just I guess as I would if I were in person together. So yeah, you're good on proctorial for this first one. Again, that's not to say that we might not use it later on, but we're going to see how this first one goes and see how it works out. Okay, so you do need to obviously log into Zoom and make sure that you have the camera on the whole time. We are going to have lecture a little bit, and I think what we're going to do is we're just going to lecture a little bit at 1:30, and we will probably knock off a little bit early, and that could give you some time to kind of get everything organized and maybe, you know, get ready to print it and, you know, kind of get your camera set up and your work area set up and stuff like that. And so we'll have sort of like a mini lecture maybe. We're just going to probably, to be honest with you, go over maybe 2 calculations and 2 examples of calculations with buffers. And then I think at that point, we'll probably call it a day for lecture. And like I said, give you a chance to kind of get organized and get everything ready to take the exam. And my anticipation is the exam probably will be taken somewhere around 3-ish when lab starts, or maybe we may even start it just a slightly before, again, just to give you a little extra time to maybe print it out and that type of stuff. So a kind of a short lecture tomorrow. And then again, we'll take a little break. You get everything set up, and then we'll roll into the exam at that point. Let's see. I think I got all that questions, I hope. So I think I saw one fly by, but in general, if you go through sort of our lectures and the examples we did in lectures and everything like that, and you understand how to do those, I think you should really be in good shape. You know, I don't try to test you on anything we didn't talk about. So I think you'll be in good shape if you understand that. Now, with that being said, it is an exam, so it's not going to be a, you know, word for word identical type of problem per se. But you should definitely understand the concepts and how to do those problems from what we did in class. And what I would say is in an exam. So you may have to critically think a little bit. But, you know, I would say it would be on par with, you know, the examples and stuff that we do in class. In general, you could probably take your exam and your lecture notes, if you took good lecture notes, and you probably could, you know, discover how to probably work out any of the problems on the exam. So again, mostly problem-based or maybe some other type of questions, but you know, you should be able to sort of figure it out based on the problems we did. Again, not going to be perfectly identical to those problems, but the core concepts behind it should be the same. All right, I think, if I'm not mistaken, I think I got everybody's question, I hope. Any other questions on anything on that? So again, a couple of reminders about today's stuff. We're going to move today's experiment, which was the Buffer's experiment, to Monday with the other Buffer experiment. And again, we might do it all, or we might do parts of each of those guys. So we are going to do those. Again, tomorrow on tap, we'll lecture for just a little bit at 1:30. We'll take a break, and then we'll take the exam. Again, cameras need to be on. And when you're done, you'll have to upload it at a reasonable amount of time. Okay. Any other questions on that stuff? All right. All right. At this point, you could call it a day. You can go study officially. So officially, you're still here, but unofficially, you could go off and study for your exam for tomorrow. I think that's a good use of your time. And other than that, I will see everybody tomorrow, I think. Yes? Okay. When you mean practice problems, you mean the lecture part for what we were lecturing here in lab? Is that what you're talking about? Yes. Yeah, it'll be uploaded. Yeah. So you can review it later. Yep. Okay, if you send a question to me, just give me a chance to go back through it and I'll take a look at it. Otherwise, if you're good, I'll see you tomorrow. If you had a question, just hang out for a sec. Let me just kind of look at it real quick, okay? Okay, I'll tell you what I'm going to do. What I'm going to do right now is I'm going to actually, I'm going to stop this lab meeting for a second. And that way I don't have to do too much editing in terms of the material, so I can post the lecture a little bit better. And then what I'm going to do in about 5 minutes, 3 minutes actually, less than that probably, about 3 minutes after I end it, I'm going to reopen this meeting and you could come back in and ask questions if you have questions and stuff like that. Again, I'm just going to do that so I can kind of keep the lecture part separate from this question and answer part so I don't have to do a whole bunch of editing, okay? So if you do have questions, give me about 3 minutes after I end this meeting and come back through the same lab link, and then I'll be happy to answer your questions, okay?